Now we get to the calculus and the trig, which is really where we want to get to. We want to know how we can manipulate this function to solve problems. Now to do that, I need to look at a few ideas first. We're using the idea of limits, and it might look like a silly limit to write down, but our sine curve, we know as x approaches 0, the sine curve approaches 0, the cosine curve would approach 1, and the tan curve would approach 0. We'll see why we need those in a sec. There's a circle which I'm going to draw in, and I'm going to, there we go, and I've drawn in a sector. Angle at the centre is x, which is measured in radians, we are assuming, and the radius is 1. What I do know is the area of that triangle must be less than the area of the sector. Okay. But if I now create another triangle by drawing in a tangent, so we know it's got to be a right angled triangle because radius perpendicular to tangent, and we can work out that the length of AB would end up being the tan of x. Well, the area of the sector must be less than that right angled triangle. Okay, well let's actually do some calculations. There's why I made the radius 1, makes life a lot easier, because all those halves will cancel and obviously 1 is 1. So I get that x is in between sine x and tan x. So the actual angle value will always be in between sine x and tan x. Now if I divide everything by sine x, then sine x on sine x is obviously 1. Tan x on sine x becomes the reciprocal of cos x. Well, as x approaches 0, 1 on cos x then, because the limit as x approaches 0 cos was 1, also is 1. So we know x on sine x is in between 1 and 1. Thus we've found its limit, and this was the limit I'm interested in. It's known as the small angle theorem. Another way of saying it is, rather than x on sine x, another way of saying it is for very small angles, the sine of x is equal to x. If you just multiply by sine x, you can see that you get that. But it's quite an important limit. X on sine x is equal to 1. It's a 3-unit limit, so they do like asking little questions like this. You go, oh, well, hang on, what if it's 5x on sine 5x and x approaches 0? The key to these limits is always making the angle you can't change, but you want to make the other piece of algebra the same. Because then when you've got the x on sine x, or in this case I've already got 5x on sine 5x, I know that's 1. So that'll just be 1. So if they gave me something like this, x on sine 3x, well, I want it to be 3x on sine 3x, not x on sine 3x. So if I make it 3x on sine 3x, I get a third times that. The 3x on the sine 3x, well, that's going to approach 1. Therefore, I get a third times 1, which is a third. So why did I need that? Because we're now going to work out from first principles what the derivative of sine x is. So function x plus h minus function x all over h. Well, sine x plus h, sine cos sine. If it's not the sine, it's not the sine. Well, let's work it out. Remember, the limit I know is h on sine h, or its reciprocal will be 1. So the first bit's okay. So actually it's the middle bit, isn't it? So the middle bit's okay because it's times sine h on h. So I know that bit. That leaves me with a common factor of sine x with cos h minus 1 on h. What's that limit? Well, if I play around with double angles, cos h would be the same as 2 cos squared h on 2 minus 1, but then subtract another 1, we get minus 2. So let's come from my double angle result. That, therefore, I can rewrite as 2 sine squared h on 2. Okay, so we've got 2 cos squared minus 2. Well, actually, it'd be the negative of that, wouldn't it? Should be 1 minus, but because it's going to end up being 0 in the end, just spoiler. It didn't matter that that's not negative, but technically, yes, that should be negative 2 sine squared h on 2. So that sine squared, it's close, but the limit I know is sine, not sine squared. So if I take the sine h on 2 out, I've now got that limit of sine h on 2 and h on 2. I know the sine h on h that'll be 1. The sine h on 2 on h on 2, that'll be 1. But it'll be multiplied by sine h on 2. H is approaching 0. Sine of 0 is 0. So that's why I say that it didn't actually matter that I had the positive instead of negative there, because it's going to end up going towards 0. So I end up with cos times 1, sine x times 0, and there's the derivative. The derivative of sine x is cos x. Thank goodness we don't have to do that each time, hey? So now I can generalise that. If I've got the sine of some function, so the function now is going to be the angle, then differentiate that function, it'll go to the front, and the sine will change to cosine. The angle doesn't change. So it'll be cos of function x. Okay, well let's now work out the derivative of cos x. So cosine x, well if I use complementary ratios, I know it's the same as the sine of 90 or pi on 2 minus x. That's handy because we now know how to differentiate sine. Differentiate the function, well the function is would be -1 when I differentiate that. So I get negative the cosine of pi on 2 minus x, but again I'm going to use the complementary ratios. The cosine becomes sine. So differentiate cosine, you actually get negative sine. And to generalise that one, so the angle is some function of x, we get minus the derivative times the sine of function x. Well, let's do tan then. Tan I can rewrite as sine on cos, and I now know how to differentiate both of those, so we can use a quotient rule. Square the bottom, so cos squared x, write down the bottom, cos x, diff the top, differentiate sine, we get cosine, minus, write down the top, sine x, diff the bottom, differentiate cos, we get minus sine x, and look what we get on top. We get that lovely relationship of cos squared plus sine squared, which we know is equal to 1, so it's the reciprocal of cos squared, which is sec squared. So differentiate tan, we get sec squared. To generalise that one, so we've got tan of some function, the derivative of that function out the front, tan goes to sec squared, the angle does not change. Okay, so let's do some examples then. So y equals sine x cubed, differentiate the angle, 3x squared, sine goes to cosine. The tan of 1 on x, so we differentiate the angle, the derivative of 1 on x is minus 1 on x squared, sec squared, and the angle doesn't change, 1 on x. By the way, do you notice how 1 on x squared I just looked at and went, oh that's minus 1 on x squared, rather than, oh, change it to x to the negative 1, because it's such a common one. Some of these you'll see time and time again, and you'll just look and go, oh, I know the derivative, that's this. The log of cos x. So it's actually a log function that I'm differentiating. The function is cosine x. So when we differentiate logs, we said it's the derivative on the function. The function is cos x. So the derivative of cos x is minus sine x on the function's cos x, so we get minus tan x. Tan to the power of 5? Remember in trig, we write the power there, so that's actually tan x all to the power of 5. So we use our anarchy, our chain rule. So bring down the power, 5, lower the power, 4, diff the inside, so tan x would be inside the parentheses, differentiate tan, we get sec squared. Ah, always very appropriate at this time of year, when you think about it, because what's on Friday? Swimming carnival. Cosy. Cos e to the x. So anyway, all right. Now, differentiate the angle. The angle is e to the x. Differentiate e to the x, we get e to the x. Cos goes to minus sine. So we get minus e to the x, sine e to the x. There, there's a few questions there to keep us going. Only a couple out of 14F, that's interesting. But then of course there'll be applications of the trick, so some curve sketching, some problem solving and things like that as well.